Hello everyone, welcome to the YouTube channel of YourPedia and Engineer Career Point. So I am Vinny Sharma, your mentor of mechanical engineering. So as you know, we were doing the solutions of the previous year question paper of BHEL, which is held on 2023. Okay, and we have already covered the question related to the thermal engineering, in which I have covered the subjects thermodynamics, IC engine, power plant, as well as heat transfer and fluid mechanics. Okay, so in the today's video, I am going to do the analysis of the theory of machine part, which is being asked in the BHEL exam. Okay, so before any delay, so let us start our today's videos. Okay, so here's our first question. So here you can see in the first question what is being asked. A rotor has a mass of 12 kg and is mounted midway on a horizontal shaft which is supported at the end by two bearings. So here we have a rotor which is installed midway on a horizontal shaft here, and which is supported at the end by two bearings here. Okay, and we have to assume that the shaft is a simply supported one here, and the bearings are 1 meter apart. And then what will be the critical whirling speed of the shaft here? So first of all, just understand what is the meaning of the critical speed here. The critical speed, whirling speed, and the whipping speed, all of those speeds are same speed here. Okay, how do we define their speed here? Basically, the critical whirling or whipping speed is that speed of the shaft when the vibrations of the shaft in the transfer direction has an infinite amount of amplitude here. Okay, so we can say when the shaft tends to vibrate in the with a very large magnitude in the transfer direction, that particular speed is known as the critical speed. This speed is also known as the whirling speed, or this speed is also known as the whipping speed here. Okay, and when we do the calculations here, we find that the critical speed of the shaft is basically equal to the natural frequency here. So we can say when the shaft angular velocity reaches equal to the natural frequency of the shaft, in that case what will happen, the infinite amount of vibration will take place in the transverse direction here. Okay, and the corresponding the shaft may fracture here. So here you have to find out the critical speed. That means you have to find out the value of the natural frequency of the shaft here. Okay, so now just see how do we calculate this. So here we already know that the value of the natural frequency is calculated by the ratio of under root of stiffness by mass here. It can also be calculated as the ratio of under root of gravity by deflection here. Okay, so now in the strength of material, you have already studied that whenever there is a simply supported shaft and whenever the load is acting somewhere in the mid of the shaft here, in that case the deflection of the shaft is given by PLQ divided by 48 EI. Okay, so that is the expression of the deflection here. So in that case, if I replace the if I replace the load with the mass here, the formula will become mglq divided by 48 EI. So that will be the formula of the deflection here. Okay, so here I can say the natural frequency of the shaft will be given by the gravity will cancel out, so it will formula will become 48 EI divided by mlq. So that will be the formula of the natural frequency of the shaft here. Okay, so in that case you just have to put the values, all the values into this final expression. So here you can see the value of E. Here you can see the value of EI. That means the axial rigidity values has already been provided to you, and that is equal to 4 kilonewton meter square. Therefore, its value is 4000 Newton per meter square here, and corresponding mass is given to you as 12 here, and correspondingly the length is given to you as 1 meter here. Okay, so here you can see the length is 1 meter here. So if you solve this entire expression, you will get your answer as 40 under root 10 radian per second here. Okay, so we can say that 40 under root 10 will be the natural frequency of the shaft, or which will be equal to the critical speed of the shaft here. So I can say the option number A is the correct answer of this part here. Okay, so now let us move to our next part. In this question, what is being given, the mechanism ABCD is given to you, and corresponding link length is also given to you here. Here you can see AB is having a length of 80 millimeter, BC is having a length of 120 millimeter, AD is having a length of 30, and CD is having a length of 100 millimeter here. So what do you want to find out? You have to mark the true statement. So here if you go all of those statements here, so it is basically asking you that what type of inversion is this. So here in this type of question, first of all you have to verify the Grasov law. Okay, and what is the condition of Grasov law? So basically the Grasov law states that the sum of the shortest and the longest link in a mechanism has to be equal to, or it should be less than, the sum of the other two links here. Okay, so that is the condition of the Grashof law. So if this condition is satisfied, so we can say the Grashof law has been satisfied here. So in this case, if you see, the value of S is given to you as 30, L is given to you as 120, and P and Q are the link of other two links here, that is 80 and 100 here. So if I simplify this, you will find the value of S plus L is coming out to be as 150 here, which is less than the sum of other two links, that will be equal to 180 here. Okay, so we can say the Grashof law has been here satisfied here. So law is satisfied. So in this case, how do we find out the inversions here? So here you first of all see that which link is being fixed here. So here you can see the AD link. The shortest link is basically opposite to the fixed link. So we can say the AD is in the worst position. So that is why we can say this mechanism is going to have a double rocker mechanism here. Okay, the AB link and the CD link are going to be oscillate here. Okay, they can't rotate completely about B and C point here. So that is why it is a double rocker mechanism. So the option number A is going to be the correct answer here in this case. Okay, so that's a very simple part. Now the next part is, what will be the natural frequency of a vibrating system shown in the figure in having the mass of 10 kg and stiffness as K1 equal to K2 is equal to 2 Newton per meter here. So here you can see in this diagram, the mass has been placed in between the two springs here. So let us suppose if you displace a mass by certain distance x here, the corresponding amount of displacement in both these springs will be same here. So we can say these two springs are basically attached in the parallel connection here. Okay, so in this case, if you find out the value of the equivalent stiffness, it will come out to be simply as the sum of K1 plus K2 here. So we can say the stiffness is coming out to be around 4000 Newton per meter here. Okay, 2 plus 2, 4 Newton, it is given in 2 Newton per millimeter here. So I have converted into the Newton per meter here. So now if you want to find out the value of the natural frequency, and the natural frequency is being asked in the hertz here. Okay, so that means you have to find out the value of the linear natural frequency, which is having a formula of 1 by 2 pi under root of K equivalent divided by M here. Okay, that is the formula of the linear natural frequency here. So if you find out, just put down all the values here, the expression will become 1 by 2 pi. K equivalent is given to you as 4000 and mass is given to you as 10 kg here. Okay, so here you can see after solving this expression, you are going to get 10 to the power 10 divided by pi hertz here. So option number B is going to be the correct answer of this part here. So that's a very simple question. Now the next question is, a shaft of 100 millimeter dia and 1.0 meter long has one of its end fixed and the other end carries a disc of mass 314 kg here, and correspondingly the radius of gyration is also given to you as 0.5 meter here. In that case you have to you have to find out the natural frequency of the shaft, and the modulus of rigidity is given to you. Okay, so now just see in this case, so basically this is a case of a torsional vibration. So if you want to find out the value of the natural frequency in hertz here, so here again you have to find out the value of the linear natural frequency. So here you can see again I can write the linear natural frequency is going to be equal to 1 upon 2 pi under root of directly you can write 1 upon 2 omega n upon 2 pi here, omega n upon 2 pi. But now in the case of the torsional vibration, the natural frequency omega n can be written as under root of torsional stiffness divided by moment of inertia here. Okay, so here you can see St is representing the torsional stiffness of the shaft and I is representing the mass moment of inertia of the disc here. Okay, so now if you just put all the values here, okay, and understood one more thing, what is the meaning of stiffness here? So stiffness in this case is going to be equal to torque required to produce a unit angular displacement here, unit angular deformation here. So it will be the ratio of the T by theta, which can be further written as Gj upon L here. Why I am writing this in this way? Because you can simply write in the form of simply torsion formula here. Okay, just wait a minute. So here in this case, if you see, the value of the omega n can be written as Gj upon L multiplied by I here. Okay, so Gj upon L is representing the torsional stiffness and I is representing the simply the mass moment of inertia. So if you put all the values into this expression, 1 by 2 pi, now the value of G is given to you as 80 giganewton per meter square. So we can write its value is 80 to the power 10 to the power 9, 80 into 10 to the power 9 here, and the value of J is nothing but it's the polar moment of inertia, that will be equal to pi by 32 d to the power 4 here. So diameter value is 0.1 here, and correspondingly the length is given to you as 1 meter, and the I is basically representing the mass moment of inertia, which is having a formula of the mr square. So mass is given to you as 314 multiplied by r square. So r is 0.5 square here. Okay, because the mass moment of inertia is having a formula in terms of radius of gyration as mr square. Okay, that will be the formula of the moment of inertia here. So if you simplify this expression, you will find the value of the natural frequency is coming out to be around 50 by pi here. So that will be the exact answer which you get here in this case. Okay, so option number B is going to be the correct answer of this question here. Okay, just simplify this expression and you will find this particular value here in this case. Now let us move to our next part. So in the next question, the essential condition of locating the two mass in order to system become dynamically equivalent is known as the, okay, so now just see, let us say if you have a simple connecting rod here. Okay, so if you see the mass of the connecting rod is uniformly distributed, okay, all over the periphery of the all over the length of the connecting rod here. So if you want to convert that model of the connecting rod into a dynamic equivalent system, so what you have to assume, so there you have to assume that the total mass of this connecting rod is concentrated at one end of a massless rod and on the other end of the massless rod here. In that condition, basically the required condition between the radius of gyration of the body and the distance of the two masses from the center of gravity is basically defined in the ratio of option number A here. Okay, so just remember that part. That is a simple formula which you get while solving the dynamically equivalent system here. Okay, next part, a vibrating system consists of a mass, a spring of stiffness 80 Newton per meter and a damper with a damping coefficient of 800 Newton second per meter here. What will be the natural frequency of the damped vibration here? So again, in this question you have to find out the value of the damped natural frequency in hertz here. So we can write the damped natural frequency will be equal to omega d upon 2 pi, where omega d is representing the damped natural frequency here. Okay, just remember that. And here you can see omega d can be written as omega n 1 minus zeta square divided by 2 pi here. That will be the formula of the damped natural frequency in hertz here. So here if you see, the value of the natural frequency can simply be written as stiffness by mass, and the value of the stiffness is 80 Newton per millimeter, that means 80,000, and mass is given to you as 200 kilogram here. Okay, so if you simplify it further, you will find the natural frequency is coming out to be as 20 radian per second. That will be the value of the natural frequency. Now again, what do you need? You need a value of the zeta here. So if you remember this simple governing differential equation, you can write, the equation is written as x double dot plus c by m x dot plus omega n square, or you can simply write s by m equal to 0. So this equation can further be written in this way also. So in that case, if you just compare these two equations, you can equate the c by m parameter equal to 2 zeta omega n. So we can say the c by m parameter is going to be equal to 2 zeta omega n and if you put all the values into this expression, you can easily find out the value of the zeta here. So value of C is given to you as 800, the mass is given to you as 200, it's 200 kg, and the value of zeta you have to find out, damping ratio, and omega n is given to you as 20 here. Okay, so if you simplify it further, you will find the value is coming out to be around 0.1 here. Okay, value of zeta is coming out to be 0.1, and if you put just put these two values into the final expression of the damped natural frequency, you will get your answer. Okay, so you just have to solve this particular expression and you will get your answer as 3√11 by pi here. Okay, so option number C is going to be the correct answer. Just do the calculation and you will get your final answer, this one. The next part, a speed of a flywheel is to be measured using the stroboscope for a single mark. After setting the 2800 rpm on the stroboscope, a stationary picture of 4 mark is absorbed here. What will be the speed of the flywheel here? So see, in this case actually what happened, stroboscope is basically a device which is used to calculate the speed of the rotating objects. Okay, it can measure the speed of a rotating object in between the 60 rpm to 20,000 rpm here. And how do you find out the speed here? So first of all, in this case, the speed of any rotating object, or I can say the speed of the body, can be calculated by the ratio of simply strobe flash frequency divided by number of marks here. Okay, so that is a simple formula for calculating the value of the speed of the flywheel. So in this case, here you can see the strobe flash frequency is nothing, it is given to you as 2800 rpm, and the number of mark is also given to you, that is we are having the 4 marks here. So we can say the speed of the flywheel or speed of body is coming out to be around 700 rpm here. So option number A is going to be the correct answer of this part here. Okay, so that's a very simple question. Okay, you just have to take the ratio of 2800 divided by 4 here. Now the next part is, which of the following is the correct analogy between the electrical and mechanical system for the vibrating system? So here you can see the first statement is the mass in the mechanical system is equivalent to the voltage in the electrical system. That is not a correct statement here. Spring stiffness in the mechanical system is equivalent to the current in the electrical system. It is not a case, because if you see the current is already flowing from one body to another, one point to another point due to the voltage difference, but in the vibrating model it is not like this here. Next point, damping coefficient C in the mechanical system is equivalent to the resistance in the electrical system. That is the correct statement, because the damping is basically representing the friction here, okay, which is dissipating the energy of the vibrating system here, okay, or I can say which is dissipating the vibrations here. So here the option number C is basically the correct option here. Okay, next part is force in the mechanical system is equivalent to the inductance in the electrical system. That is also a incorrect statement here. Next question here. Dunkerley empirical formula to find the natural frequency of the transverse vibration for a shaft carrying a number of point loads here, and uniformly distributed load is given by. So here you can see this is a basic direct formula based question here. Okay, if you have a just basic idea that what is the expression of Dunkerley formula, you can solve this question, and in this case the expression is given by 1 upon fn square equal to 1 upon fn1 square plus 1 upon fn2 square and so on. Okay, basically it is a case where you are assuming that we have a shaft and it is acted upon by a uniformly distributed load. In that case, what will happen, due to this all over the point load, what will happen, there will be certain amount of deflection here, and according to that certain amount of deflection at each and every point, you can calculate the corresponding values of the natural frequencies here, fn1, fn2, fn3. And if you want to find out the entire natural frequency of the system, you can simply use this particular expression here. Okay, so that is a direct formula based question. Next part, for a small value of the damping ratio zeta, the dynamic magnification factor at resonance is given by. See, first of all, at the resonance, the omega is going to be equal to omega n here, and we already know the magnification factor is having a formula of 1 upon 1 minus omega by omega n square ka whole of square plus 2 zeta omega by omega n. So that is the expression of the magnification factor. So here if you see resonance condition is given, that means the frequency ratio omega by omega n is going to be equal to 1 here. Okay, so if it is 1, so we can say the first term is going to be 0. So this first term is going to be 0 here, because 1 minus 1 is going to be 0 only. So we can say the magnification factor is going to be equal to 1 upon 2 zeta here. Okay, so option number C is going to be the correct answer of this part here. Okay, so let us move to our next part. In the longitudinal vehicle car dynamics, which of the following forces is insignificant external longitudinal force acting on the vehicle? See, in the case of a simple longitudinal vehicle car dynamics, longitudinal tire forces, aerodynamic drag forces, rolling resistance, it is going to have a very large value. Okay, but if you see about the buoyancy forces, the buoyancy forces is due to the displacement of the air here. Okay, because the car body is basically displacing the air by a certain amount, and the corresponding buoyancy forces magnitude depends upon the density of the air, and the density of the air is having a very small value. So we can say the buoyancy forces is negligible in the case of longitudinal vehicle dynamics here. Okay, so option number C is going to be the correct one answer here. Next part, which of the following is the correct full name of the SCARA type of robot? That is a simple question here. So here the selective compliance assembly or articulated robot arm is basically the full form of this SCARA type of robot here. Next part, a machine is coupled to a 2-stroke engine which produces a torque of 800 plus 180 sine 3 theta here. So this is the torque produced by the engine, and here you have to calculate the power of the engine here. Okay, if the mean speed of the engine is given to you as 600 rpm. So now how do you solve this question? First of all, just remember the power is nothing but is given by the product of mean torque multiplied by the mean speed here. So that is the basic formula of the power. So that means you have to calculate the value of the mean torque. Now how do you calculate the value of the mean torque here? Mean torque is calculated by the ratio of the total work done, okay, during a cycle divided by the total period here. So we can say the total work done will be T d theta, integration of T d theta, or we can say area under curve of turning moment diagram divided by the period here. So here the 2-stroke engine basically complete its cycle during the 1 revolution of the crank. So we can say the period is going to be equal to 2 pi only. Okay, so you have to perform the integration from 0 to 2 pi, then you have to calculate the value of the mean torque, and then you have to calculate the value of the power itself. So here you can see, if you put all the values into this expression, you will find 800 plus 180 sine 3 theta. So this will be the torque here, and correspondingly the period is 1 by 2 pi. So if you simplify it further, you will find 1 by 2 pi integration is going to be equal to 800 multiplied by 2 pi minus 0. Okay, the integration of 180 sine 3 theta is going to be equal to simply minus 180 cos 3 theta by 3 here. So that will be the integration of 180 sine 3 theta. So we can say it is coming out to be around minus 60 cos of 6 pi minus cos of 0 here. Okay, so that will be the integration. Okay, so if you see here, cos of 0 is equal to 1 and cos of 6 pi is also equal to 1 here. So we can say this entire term is going to be equal to 0. So therefore the mean torque is coming out to be around 800 only. Okay, the mean torque is coming out to be 800 Newton meter, and simply we can say the power is going to be equal to mean torque multiplied by the mean speed. So mean speed is 600 rpm, so we can say it will be 2 pi 600 by 60 here. So if you simplify it further, you will find your final answer here. Okay, and answer you will be getting as 50.24 kilowatt here. Okay, that will be the exact answer of this particular question. So actually this is a very simple question here, if you have just basic understanding of how to calculate the power here. Now the next part is, a cam is to give the following motion to a knife edge follower here. In this case, follower motion follower move to a rise through 40 millimeter during the 90-degree rotation of the cam here. So we can say the lift is given to you as 40 millimeter here, and corresponding angle of ascent is given to you as 90 degree. Okay, along with that, second statement is follower to dwell for next 45 rotation for the cam. So we can say the dwell angle is given to you as 45 degree. Next part, follower to return to its original position during the next 120 degree of revolution here. So we can say the angle of descent is given to you as 120 degree in this case. And the next part is follower to dwell for the remaining period. So we can say 120 plus 90, 210 plus 45, that is 255, and it will be equal to 105 degree here. Okay, so there are two dwell of 45 degree and then a dwell of 105 degree here. So what do you want to find out? The follower moves with the simple harmonic motion during the rise as well as the return stroke, and the least radius of the cam is 50 millimeter here. What will be the maximum velocity of the follower during the rise if the angular velocity is 30 radian per second here? So in this type of question, you just have to remember the basic formula of the maximum velocity, maximum acceleration and displacement during the different types of motion. There we have a 4 types of motion here. Okay, so here you can see in this case, if, whenever the follower is having a simple harmonic motion, we can say the velocity is going to be maximum velocity is going to be pi by 2 omega s by theta naught here. Okay, because we are calculating the value of the maximum velocity during the rise here. So let us suppose if you want to find out the value of the minimum maximum velocity during the return stroke, so here you will be having the theta r here. Okay, so now just see, omega is given to you as is given to you as 30 radian per second. Corresponding lift, S is representing the lift of the follower here. So in this case, the lift is given to you as 40 millimeters. So I can write it will be 0.04, and theta naught is given to you as 90 degree. So you have to convert this into the radian here. So we can say if you solve this expression, this numerator will be cancelled out with the denominator. So we can say the 30 into 0.04, it will come out to be 1.2 meter per second here. The 1.2 meter per second is representing the maximum velocity here. So option number A is going to be the correct answer of this part here. Okay, next part, in a slider crank mechanism, the length of stroke is 2r and that of the connecting rod is L here. What will be the angular velocity of the connecting rod if the crank rotate at an angular speed of omega here? Okay, so that's a very simple question here. In this case, you can see if I simply draw the single slider crank chain mechanism, that will be the diagram here. Okay, so in that case, let us say the crank is making an angle of theta and crank is rotating with the angular velocity omega here, and the connecting rod is making an angle of beta here. Okay, so how do you find out the angular velocity of the connecting rod? So first of all, just see the angular velocity of the crank is nothing but it is equal to the rate of change of angular displacement with respect to time. So we can say the omega of the crank is d theta by dt here. Similarly, if you carefully see the diagram, here the connecting rod is making an angle of beta here. So that means the rate of change of angular displacement, that is beta, with respect to time is going to represent the angular velocity of the crank here. Sorry, angular velocity of the connecting rod here. Okay. So here if you see this vertical line is going to be common in both of these triangle here. Okay, let us say if I do the naming here, A, O, B. So here you can see from triangle A, B, C and triangle AOC. In both of these triangle, this AC line is going to be common. Okay, so I can write simply, this is L here, this is R here. So I can write L sine of beta is going to be equal to R sine of theta here. So we can say the sine of beta is going to be equal to R upon L sine of theta here. Okay, and the ratio of the connecting rod length with respect to the crank radius is nothing but it is equal to the obliquity ratio. So here this relation will come here. Okay, so now in this case, if you just differentiate these two terms, differentiate this expression, you will find the cos of beta multiplied by d beta by dt is going to represent you cos of theta d theta by dt divided by n here. So that will be the expression here. So can I say that the d theta by dt is representing the angular velocity of the crank and d beta by dt is representing the angular velocity of the connecting rod. So I can write the angular velocity of the connecting rod will be equal to cos of theta divided by n cos of beta multiplied by angular velocity of the crank here. Okay, so and one more thing here, sin of beta you already know. Okay, so I can write sin square beta plus cos square beta is going to be equal to 1. So I can write the value of the cos of beta is going to be equal to this one here. So if I just put this expression here in this case, you will find the angular velocity of the connecting rod will become omega cos of theta divided by n multiplied by under root of 1 minus sin square beta here. Okay, and if you replace this sin of beta with the sin theta by n, you will find the value of the angular velocity of the connecting rod will comes out to be omega cos of theta divided by n under root of n square minus, sorry, it is not coming out to be this one. This will come out to be as n square minus sin square theta here. Okay, that will be the final expression of the angular velocity of the connecting rod here, omega cos of theta under root of n square minus sin square theta here. Okay, so option number D is going to be the correct answer of this part here. So that's a very simple question actually. Okay, you just have to have a basic understanding of how to proceed here. Next part, the acceleration of the particle is given by a is equal to 10 minus x here. The particle starts at time t equal to 0 with no initial velocity at x equal to 0. So we can say at x equal to 0 we are going to have initial velocity as 0 here. Okay, along with that at x equal to 0 v1 is going to be 0, that is okay. What will be the velocity of the particle when the acceleration is 0? Okay, so if you see at x equal to 0 we are going to have initial acceleration also as 10 here. Just put the value of x as 0 here, you will find out the acceleration also. Okay, so now what do you want to find out? You want to find out the value of the velocity of the particle when the acceleration is 0. So here you can see acceleration, where the acceleration will be 0. Acceleration is given by 10 minus x and it has to be equal to 0. So we can say at x equal to 10, at x equal to 10 meter you are going to see the 0 acceleration value here. Okay, that means we have to find out the velocity of a particle at 10 meter distance here. So okay, so how do you proceed here? So first of all, just see here in this case, acceleration is equal to rate of change of velocity with respect to time here. That is how you calculate the value of acceleration. But now the problem is the velocity is not changing with respect to time, the velocity is changing with respect to the distance, and the distance is correspondingly changing with respect to time here. So we can say the A is equal to dv by dt. It can be written as dv by dx multiplied by dx by dt here. Okay, and you already know the acceleration is given as 10 minus x here. dv by dx you don't know, but the rate of change of displacement you already know, it is equal to velocity here. Okay, so if you just simplify this expression, you will find the v dv is going to be equal to 10 minus x into dx here. And if you just simply integrate this expression, you will find v square by 2 is coming out to be as 10x minus x square upon 2 plus constant here. Okay, so in this case, if you see, we already know, see here we have a constant and we have to find out the value of this particular constant with the help of boundary conditions. So here we have a boundary condition, that is at x equal to 0 we are going to have a 0 velocity. So if you put the value of the x here 0, you are going to have a 0 velocity here. At x equal to 0, v is going to be 0 here. So we can say 0 is equal to 10 multiplied by 0 minus 0 square by 2 here plus constant. So from here you can see the value of constant is coming out to be 0 here. Therefore I can write the velocity will come out to be as 20x minus x square under root. So that will be the relation between the displacement as well as the velocity here. Okay, you just have this, you just simplify this particular expression by putting the value of c as 0 here. Okay, so here you can see 2 multiplied by 10x, 20x, this will be minus 2x, that will be x square here, and you have to take the under root to calculate the velocity here. So I can write at x equal to 10 meter, the corresponding velocity will comes out to be 200 minus 10 square. The answer will come out to be as 10 meter per second there. So option number A is going to be the correct answer of this part here. Okay, so that's a very simple question in this case. So that's a question from the basic mechanics here. Next part, a wheel accelerates uniformly from rest to a speed of 300 rpm in 1 second here. Okay, how many revolutions will be made by the wheel during this interval here? So in this case, initial speed is given to you as 0, okay, and the final speed is given to you as 300 rpm. So I can write the omega 2 will be 2 pi 300 by 60 here. So that will be equal to 10 pi here. Okay, and the time taken is equal to 1 second. That will be the time taken. So how many revolution will be made here? So here you can see, if you just use a simple expression, so I can write omega 2 is going to be equal to omega 1 plus alpha into t, and omega 2 is given to you as 10 pi, omega 1 is 0 and alpha is you don't know, and the value of time is 1 second. So we can say the acceleration is going to be equal to around 10 pi here in this case. Okay, so wheel is accelerating with the angular acceleration of 10 pi radian per second square. 10 pi radian per second square in this case. So now how do you want to find, what do you want to find out? Do you here you want to find out the number of revolutions here. That means you want to find out the angular displacement covered by the wheel here. So I can write theta is going to be equal to omega 1 t plus half alpha t square. So I can write that theta is going to be equal to 0 plus half, alpha value is 10 pi, time value is 1 here. So therefore the answer will come out to be as 5 here, 5 pi here. That means the angular displacement is around 5 pi here. So you can see during the one revolution of the crank, how much angular displacement will be covered? 2 pi will be covered here. Okay, so 2 pi will be covered in 2 pi theta is going to be covered in one revolution here. So here you can see how theta is going to be equal to 1 by 2 pi revolution here. So here how much theta is basically covering? The theta is covering to be around 5 pi here. So we can say the 5 pi is going to be equal to 5 pi divided by 2 pi revolution here. So therefore the number of revolution is going to be equal to 2.5 revolutions here. Okay, so we can say here in this case the wheel is making a 2.5 revolution in this case. Okay, so option number A is going to be the correct one. Next part, A vibrating system consisting of mass 200 kg and corresponding spring of stiffness as 80 Newton per meter. You have to calculate the value of circular frequency of undamped vibration here. Okay. Now what will be the value of the circular frequency? So here in this case, again you have to find out the value in the radian per second. So we can simply write omega n is nothing but it is equal to S by m, and the value of S is given to you as 80,000 divided by m. M is given to you as 200 kilogram. Okay, so if you simplify it, you will get 20 radian per second here. So in this case, the option number A is going to be the correct one here. Okay. Okay, so now just see the next question. In this question, what is asked? The slider crank mechanism is shown in the figure. It has link 1 as a fixed here. Okay, so here we have a link 1 as a fixed and link 2 is a crank here. And now if in place of link 1, link 2 is getting fixed here. That means initially we are having the link 1 as a fixed here, but now instead of 1, what we are doing, we are fixing the link number 2. So here we are fixing the link number 2. Then what will happen here? So in this case, what will happen? So here you can see now the inversion will be different here. So again, whenever you are fixing the crank here, you get two different type of inversions here. The first one is known as the Whitworth-Quick return mechanism and the second one is known as the rotating engine basically. Okay, so here you can see out of these four options, the option number A, Whitworth-Quick return mechanism will be the correct answer. Okay. Okay, so here we have completed all the questions related to the theory of machine which has been asked in the BHEL exam of 2023. Okay, so hope you can see the questions are very good. Okay, the lot of numerical has been asked in the previous year exam. Okay, along with that you will find that the number of questions has been asked from the vibration chapter. Okay, so be careful, you have to cover up the vibration part very carefully. Okay, so just have a basic understanding of each and everything in the theory of machine. Along with that, practice the numerical also. Okay. And also one more thing, I am again repeating that don't expect the calculator is going to be provided to you. Okay, maybe the calculator will be there, but because in most of the numericals they are providing you the values here, assumed values. Okay, so that your calculation will get simplified. So that means you are not going to get a calculator there. Okay, so please be made sure of that. Okay, so that is for today's videos. Okay, so thank you very much.